Hi guys, we are going to start chapter 3 today on determinants. So if we were in class, I would ask you to read this to me, but since not, I'll just read it to you. In his autobiographical book, Surely You're Joking, Mr. Feynman, the Nobel Prize winning physicist Richard Feynman tells of observing ants in his Princeton graduate school apartment. He studied the ants' behavior by providing paper fairies to sugar suspended on a string where the ants would not accidentally find it. When an ant would step onto a paper fairy, Feynman would transport the ant to the food and then back. After the ants learned to use the ferry, he relocated the return landing. The colony soon confused the outbound and return ferry landings, indicating that their learning consisted of creating and following trails. Feynman confirmed this conjecture by laying glass slides on the floor. Once the ants established trails on the glass slides, he rearranged the slides and therefore the trails on them. The ants followed the repositioned trails, and Feynman could direct the ants where he wished. Suppose Feynman had decided to conduct additional investigations using a globe built of wire mesh on which an ant must follow individual wires and choose between going left and right at each intersection. If several ants and an unequal number of food sources are placed on the globe, how likely is it that each ant would find its own food source rather than encountering another ant's trail and following it to a shared resource? In order to record the actual routes of the ants and to communicate the results to others, it is convenient to use a rectangular map of the globe. There are many ways to create such maps. One simple way is to use the longitude and latitude on the globe as x and y coordinates on the map. As is the case with all maps, the result is not a faithful representation of the globe. Features near the equator look much the same on the globe and the map, but regions near the poles of the globes are distorted. Images of polar regions are much larger than the images of similar sized regions near the equator. To fit in with its surroundings on the map, the image of an ant near one of the poles should be larger than the one near the equator, but how much larger? Surprisingly, both the ant path and the area distortion problems are best answered through the use of determinants, the subject of this chapter. Indeed, the determinant has so many uses that a summary of the applications known in the early 1900s filled a 4-volume treatise by Thomas Muir. With changes in emphasis and the greatly increased sizes of matrices used in modern applications, many uses that were important then are no longer critical today. Nevertheless, the determinant still plays an important role. So this chapter, we're going to be studying determinants. So we have the definition of determinant. You all have worked with the determinants before, but basically the principal property states that if the determinant does not equal 0, matrix A will have a unique solution. And equivalently, if determinant A does not equal 0, if and only if matrix A is invertible. So you could essentially add this to the invertible matrix theorem, that a matrix is invertible if and only if the determinant for A does not equal 0. And that's something we kind of knew before, but this chapter will just solidify our knowledge of determinants and expand. So we're going to look at how to find the determinant for both 2 by 2 and 3 by 3 and then even 4 by 4 matrices today. So what we are going to consider is first looking at the determinant of A, where the matrix is defined by A, B, C, D, listed thusly. What it is it's denoted by these vertical brackets here and here. That means you're finding the determinant. And with a 2 by 2, it is simply AD minus BC. It's just the one diagonal minus the other diagonal. Now, if you have a 3 by 3, we've gotten some experience doing this. You can either use this formula or you can kind of imagine this pattern. So for the positive values, the values we're going to take as positive, you're going to take the diagonals going in the main direction. So you have one diagonal and then you go up one. Now, if you go up one above that diagonal, notice you only have two entries. So we have to grab our third entry that has rotated down below. And then if we go up one again in the same direction, we only have one entry left. And then it is times these two entries, which have again rotated down below. So those are your positive entries. Your negative entries are considered going in the opposite diagonal direction. So you go the opposite diagonal, then you go one above it, scrolling down one above that, and then we have to scroll down again. And those are multiplied together, and then those are all treated as negatives. And then you add the positives together, the negatives together, add those, and then you get the determinant. So we are going to do this with an example so that you guys can see this in action, because just looking at stars and rectangles is probably not all that effective. So take this particular matrix. I know that it is asked of me to find the diagonal because I have these vertical lines surrounding the matrix. So the pluses are the ones we do on the main diagonal. So it's 3 times 1 times 1. So that's going to give us a 3. Then, and I'm actually going to use another color just to differentiate since I'm not looking at the same, I'm looking at the same matrix. I go up 1. So up 1, I get 2 times -3 and then times 4 because I need 3 in every diagonal row. So it's 2 times -3 times 4. So that's going to give us -24. And then plus, now I have to go up 1 on my main diagonal. And with the up 1, I only get 1 in that above diagonal. And then here I have to go down below. And you can see that the product of those will be 0 because there is a 0 in my diagonal. I'll just call it a diagonal row. So here for the positives, we get -21, adding up 3 and -24. Now for the negatives, you have to go in the opposite direction. So in the opposite direction, we would have this, which kind of crosses out my my view. So what I'm going to do is just erase so I end up with a clean matrix to work with. So I'm going to go the other diagonal to do my negatives. So I do 4 times 1 times 1, which yields 4. And then plus, now I'm going to go up 1. So you get 2 in that row, so I have to add to the next row. So that's 2 times 2 times 1, which is 4. So we have 4 plus 4 plus, and then we meet our last diagonal row, which I'll have to repeat the yellow here for. And that one is going to be a 0. So now when I combine those, I get, when I combine those, I get 8. And so it's -21 and then -8 because this is minus from here. So that means my determinant is -29. All right, so it is -21 -8, or you can think of it as -21 plus -8. Okay. So there is my determinant using, I call this the diagonal rule. So now I'm going to show you a different way to look at this process, the way that you probably learned before. And if you go deeper into the diagonal rule, you'll see that these are actually exactly the same. It's very interesting comparing the two methods if you want to do it with like just replacing the numbers with letters for the different elements. But the rule you learned was using the submatrices rule, where basically you take one row or one column of the matrix. So one row or one column of the matrix. Um, and so I'm just going to take the first row. So you take the very first element in the first row, and that gets multiplied by the submatrix that is created by crossing out the row in the column that is in. So if I take A and cross out the row in the column that is in, I have this resulting mini matrix or submatrix. Okay, so that's how I get my first term. And then my second term, I would go for B, just going along that row. And then if I cross out the row that B is in the column that B is in, I get the mini matrix generated by B. And then C would be the same thing. C, if I take C, cross out the row and column that C is in, and then I get the mini matrix D, E, G, H. Now there is a pattern to this with determinants. It's always going to be a plus, minus, plus pattern if you are in the first row. There is a bit of a caveat because if you're not taking your coefficients from the first row, it will change. So I'm going to show you what that is. Essentially, the way it looks, if it is a 3 by 3, is the first row is plus, minus, plus for your coefficients. So A is positive, B is negative, C is negative, C is positive, but then it's minus, plus, minus if you take the second row, and then plus, minus, plus if you take the third row. So if I say, okay, I want to take the coefficients from my first row, it'll be plus, minus, plus, but you could easily just take your coefficients from another row or another column. You might be asking yourself, well, why would you want to do this? Let's say one row has several zeros in it, or one column has several zeros in it. You could just use that column and it will make your work a lot more less lengthy. So if we take a look at this matrix, which if you go here, it is it the same? Yeah, it's the same. That's great. Then we can check our answers. We're going to use the cofactor. It's another way, but we'll call it the mini matrix method of calculating the determinant. So I'm going to look at the first row. The first row is 3. The first element in the first row is 3. And so then I imagine myself crossing out that row in that column that 3 is in, and then I generate a mini matrix. Okay. Next, I'm going to go along the row to the next element. And so because of the plus, minus, plus nature, that's going to be minus 2. And then in that row, I cross out the elements. And in that column, I cross out the elements. So the mini matrix is 2, 4, negative 3, 1. And then moving on to my last element in that row, which would be 1, it's going to be plus 1. And then to generate my mini matrix, I'm going to cross out the row and the column that 1 is in, and then I get 2, 1, 4, 0 for my mini matrix. Now notice when you do these mini matrices, you're not creating actual matrices, you're just indicating that you're finding the determinant of that matrix. So now I'm going to find the determinant of the matrices. So this is just going to be 1 because it's 1 times 1 minus 0, and then minus 2 times, and this is 2 times 1, which is 2, minus negative 12. So that's going to be 14. And then plus 1 times negative 4. So simplifying, it's 3 minus 28 minus 4, which is going to be negative 32 plus 3, negative 29. What? So if we look, oh, I'm like blocking my work here. Negative 29 is right there. And then if we go back here, do you guys see how we got negative 29? Negative 29. And if you do this with just the elements being the letters to just generalize it, you'll see why the diagonal method is actually the exact same as the cofactor method. It's kind of, the diagonals are found, let me get rid of this blocking here. You'll notice, like, if I'm doing one diagonal, let's say, I consider the diagonal method and I do this way is just 3 times 1 times 1. That's what here is the same as here. And then you just keep going. And then the other way are the minuses. It's really quite neat. So you can use the sub matrix method. We'll learn it as cofactor another day. But you can use the sub or mini matrix method, mini matrices method for any matrix, any square matrix. However, the diagonal method is only going to work for 3x3s. So the 3x3s are quite popular. So that's why the diagonal rule is cool, because they end up showing up all the time, because consider the space that we live in is 3x3. So the diagonal rule is only for 3x3s. The submatrix method is for any matrix at all. So that's where it's a little more generalizable. So yeah, pretty cool. You guys ready for a 4x4? Sorry, I'm making faces and you can't even see me, but I am ready for a 4x4. So let's do this. So recall that we're going to do the cofactor. So we're going to do the mini matrix. We want to choose wisely. So pick a row and column that has a lot of zeros in it, because that's going to be, oh man, or maybe we should just do it the regular way. I don't want to confuse you guys. Yeah, we'll just do it the regular way. And we might not get the answer, but at least we'll set it up, because these are going to be crazy. So it's going to be 1 times the following. So again, to find it, I'll cross out the row and column that the 1 is in, and then I'll generate my sub matrix. Okay, and then it's a plus minus situation. So that's my positive. So now I'm going to go through. We'll do minus 2 times the following. And I'm going to cross out the row and the column that the 2 is in, just so I can really see the mini matrix. Okay. So that's the second coefficient from the second element in that row. And then let's do the 3. So it's plus minus, and then this is plus 3 times, and then the row that 3 is in gets crossed out, the column that 3 is in gets crossed out, and I generate the mini matrix. Ooh, I'm almost there, you guys. And then lastly, in that row, I have a 4. So in the column in the row that the 4 is in. I'll cross everything out. And there's my mini matrix. So what I would do if we were in class is I would assign two of you to find the determinant of each matrix. And then you'd multiply. Ooh, you see my mess up? It's -4. Sorry. I got lost there in my plus minus plus minus. And then I have it, right? So that is it. I don't have the answer for this one. So that's unfortunate. Ooh, maybe I have this written down on a random post-it note. So let's write it down. So check my work. But yeah, because now that you have the mini matrices, I would probably use the diagonal method to do the determinants of all these 3x3s. And then it's 1 times the determinant of the first one minus 2. And on a sheet of paper, I have that listed. So yeah, maybe it is, maybe it isn't. You can always check these in your calculator, but do know for homework and for tests, I'm going to be forbidding calculators because the calculators are there for you to find the matrices, but I need you to kind of be able to do it by yourself. So yeah, let's hope that's the answer, but I think you get the drift here. One thing I wanted to point out is that if we wanted to go with a row or column with more zeros in it, therefore generating a little less work, is you could have, and you guys, I'm going to clear this out, so hopefully you had it written down. So if you wanted to, you could have chosen this column right here. So this column, we're at plus minus, this is plus. So 3 is going to be positive going down this column. And then if I cross out the rows in the column here, my mini matrix for 3 is going to be -1, 0, 2, 2, 4, 4, and then 5, 6, 6. Oops, sorry, that should not be curvy. And then it would be minus, because this is plus, so this is -0. Don't have to do that one, haha. And then plus -2. So let me get rid of this stuff. Keep that here. So if we do -2, here's the colorizing of my 3. The 0 is nothing. Here's the -2, so it's plus -2. And then if I cross out the row that -2 is in, and the column that -2 is in, I would get 1, 2, 4, -1, 2, 5, 2, 4, 6. So that was my plus -2 and then -0. And I don't need, doesn't matter. So that means I only have to find the determinant of 2 3x3s instead of 4 3x3s. So that's where it's really cool to choose a row or column with a lot of zeros because it minimizes your work. So that's what I was considering when I talked about choosing your rows and columns, is that you can choose wisely and generate less work for yourself. Okay, so hit me up on Zoom if you have questions. So here's our summary. For a 2x2 matrix, the determinant is AD minus BC. For a 3x3 matrix, this is just the whole description of how to do that. And then it references the plus minus pattern that we talked about. We talked about finding upper and lower triangular matrices before our spring break, which seems like it was years ago, but either way, upper triangular is where the diagonal and everything above it are generally non-zero quantities, but below the diagonal is all zero quantities. That is the upper triangular matrix. And a lower triangular matrix is just the opposite. It means all of the interesting parts are in the lower part of the matrix. Now, cool thing about upper and lower triangular matrices is that the product of the diagonal is the determinant. And the reason it is, you can still go through all the steps, but the zeros effectively cancel out all the rest of it. So the determinant is simply the product of the diagonal. And it's also true for a lower triangular matrix. So we're going to be using these facts when we learn some more properties of determinants. So that's super cool. Okay, so here's a practice problem just to give you a quick look-see for this one. You'll notice the third column is all mostly zeros. So the only number we have to pay attention to is the 2, and then develop the mini matrix. This is so great. And it's going to be a positive 2 because it's plus, minus, and then plus. But if I cross out that row and then that column, I can do my mini matrix. So that's 0, 3, -4, -5, -8, 3, 0, 5, -6. Okay, and then with this, I'm going to do the diagonal method. So going in this direction, and I still have to remember to do the 2 on the outside. So for pluses, I would get 48 plus, and then if we go 1 above that, it's 3 times 3 times 0. So that's going to be 0. I need to colorize my 48. Right. And then going 1 above that, I have -4 times -25. That's going to be 100. So we have 148. If I did that right. Yeah, I don't see anything wrong with that. Okay, so there's my positives. Then my negatives going in the other direction. I think I'm just going to circle going in this direction. So my main diagonal is just 0. Then if I go 1 up from that, I feel like I did something wrong. Is my first diagonal? Oh my gosh, you guys. Sorry, this is 0. I don't know what I was thinking there. So that's just 100. So this diagonal is 0. Then I'm going to do my oranges. I have -15 times -6. So positive 90. Did I do this right, you guys? Sorry, I know you're not here to guide me. Yeah, I mean, that's 90, and then plus, and my last one in that direction will be 0. Okay, so you subtract those because it's the positives. Here's my positive right here, and my negatives, so those get subtracted. That's 10. So 2 times 10 is 20. So that should be my determinant. So coolio, there we go. Rhyming. Okay, well, I hope you guys are doing well. Coronavirus. This is a cool fact, so I'm going to read it to you. The homework's right there. EOO stands for every other odd. So by today's standards, a 25 by 25 matrix is small, yet it would be impossible to calculate a 25 by 25 determinant by cofactor expansion. In general, a cofactor expansion requires over n factorial multiplications. And 25 factorial is approximately 1.5 times 10 to the 25th power. If a computer performs 1 trillion multiplications per second, it would have to run for over 500,000 years to compute a 25 by 25 determinant by this method. Fortunately, there are faster methods, which we will soon discover. Very exciting. All right, hope you guys are having a good day, and I will see you when I see you.